Hello my schoolers, you welcome to my school YouTube channel. My name is Manuel. This video will be tackling JAMB CBT past question in chemistry for the year 2005. Please don't go anywhere, stick around and we'll be right back. You welcome back to my school YouTube channel. In today's video, we'll be tackling question 26 to question 50. Now let's get down to question number 26. The shape of the hydrocarbon compound CH4, of course that's your methane, is what? We have square planar, we have planar, we have linear, we have tetrahedral. The shape of the hydrocarbon compound of methane actually is tetrahedral. The reason being that the VSEPR, okay, theory can explain that. VSEPR, valence shell electron pair repulsion theory. And what does it state? It's saying that the electron pairs will arrange themselves around the central atom in such a way that they will minimize the repulsion. Usually when we have atoms, okay, electrons that are surrounding the central atom, usually there's a kind of repulsion, okay, between them or among them, okay, depending if there are two, if there are three. So what happens is that the electron pairs will so arrange themselves in such a manner that they will minimize the repulsion that should take place between them and the central atom. So that usually gives rise to the type of shape that they have. For instance, we talk about methane. Methane undergoes the sp3 hybridization. When we say sp3 hybridization, it means it is formed from one s orbital and then we have three p orbitals, okay, actually forms that, having a bond angle, of course, in equal angles of about 109.5 degrees, okay. So if you have that, that is what is responsible for the tetrahedral shape of the methane owing to the VSEPR theory. So that is what is responsible. So based on that, the correct answer is tetrahedral. Option D is the correct answer. Question number 27. Which of these properties gives a solid its definite shape? Which of these properties gives a solid its definite shape? Don't forget that solids, okay, the three states of matter that we have, mainly major ones, we have the solid, we have liquid, and then we have the gaseous state. And then we know that substances that are solid, usually they have properties of having definite shape, they have definite volume based on the kind of particles, okay, that made them. When we say particles, we talk about the atoms, we talk about the molecules, okay, that make up that solid. Usually they are compacted together and it's as a result of nothing else, but they have a strong intermolecular attraction in between them, okay, that binds the particles or the atoms of that solid together. So it gives the shape of the solid. The question says which of these properties gives a solid its definite shape. There's no other thing based on what? The intermolecular forces that is of attraction between them, okay. They are very strong, that they can overcome no matter the thermal energy, the heat that is coming, it can still bind them together. It takes a longer heat, okay. That's why that is what is responsible for what? For the high boiling point of the solid substances. So you can see this, the high boiling point. What is actually responsible for the high boiling point is also owing to the fact that they have strong intermolecular attraction, okay, that binds them together. Yes, we can say maybe some of them, have high melting point because of this intermolecular. The molecules that binds them together are actually strong. The attraction between them. It is not the high melting point. It is not the high boiling point. Okay, it is not weak, of course. The intermolecular attraction in solids are not weak, they are strong. So the correct answer is option A, strong intermolecular attraction. Now on to question number 28. Sugar is separated from its impurities by what? Don't forget that sugar could be gotten, of course, in mixture, okay, like we have it in sugar cane. We have several kinds of sugar, actually, carbohydrates, whether they are monosaccharides, whether they are disaccharides, whether they are polysaccharides, okay, whether they are oligosaccharides, whatever the type, okay. Sugar usually, how do you separate them? Option A says precipitation. Now you can't separate by precipitation. Precipitation can only be evolved as a method of separation technique, okay, in mixture, okay. If we have a solid that is insoluble, okay, so if you bring in a substance to react with it, it precipitates, it forms precipitate, it is insoluble in it, we can have it. That is not sugar, so this will not be crystallization. Yes, crystallization, because if we are looking to get a pure substance, don't forget sugar is separated for what? It's what? Impurity. So which means that there are what? Impurities. Impurities might not necessarily mean that what are there, the other things that are there are not so. It's because it is not what we actually wanted. Okay, if what our aim in the mixture is to get sugar, every other thing that is there, whether it is water, whether it is moisture, whether it is maybe dirt or whatever, they are all referred to as what? Impurity. So how do we get the pure substance of that sugar? It is what? Crystallization. Crystallization brings about a pure substance. We can get our pure substances, okay, from what? Crystallization, because by the time you apply it, okay, water vaporizes, and then what we have left will be the crystals of the substance that is in the pure state. Okay, so crystallization definitely can be, sugar can be separated from its impurity by crystallization. Let's look at option C. Says distillation. You can't distillate, because if you distillate, water vapor in distillation will involve distillation process will involve boiling, okay, and condensation. Okay, if you boil, you have the water, if you have the sugar going off, and then to get it back, it might take a while. So distillation, yes, even though it is a method of getting pure substances, but for sugar, it's not going to give us that, because of what? We are looking at higher purity, to remove the purity level. Option D says evaporation. We cannot evaporate. If you evaporate sugar in the mixture, it's going to lead to what we call charring. Okay, charring of sugar. It is applied, and then it is applied. What happens? The water vapor vaporizes, and then carbon is formed. Water is formed, and then you have charcoal. Well, of course, that's what it is. So it now becomes blackened. You have a black sugar, because it is what? That's what we call the charring of what? Of sugar. So that will not give us a pure substance here. So among these separation techniques, okay, sugar is separated from its impurities by crystallization. Option B is the correct answer. Now let's move on to question 29. The component of an atom that contributes least to its mass is the what? Of course, you know we have atomic particles of an atom. We said we have the electrons, we have the protons, and then we have the neutrons. Usually we have the neutrons and the protons making up the mass, because they are found at the center, in the nucleus of the atom, and nucleus is at the center of it. So that carries more of the what? Of the mass of the element. So what determines majorly the masses of the atom of an element is the nucleus, and in the nucleus is where we have the proton and then the what? The neutron. Okay, electrons usually will be revolving around the shell, okay, moving in orbit that way, going round and round and round and round. So the mass of that, of course, is minimal. We have about 1 over 1,840 or thereabout. Of course, so negligible, okay, compared to the masses of proton and nucleus. Option A says proton. Proton is a major, okay, because proton is found in nucleus. Like I explained, nucleus is at the center of the atom. Okay, so this is the major, what is responsible for the mass of the atom of an element, and proton is found in it. Option C says neutron. Neutron and proton are both found in the nucleus, so they all determine the mass, the major component of the atom that contributes to the what? Mostly to the mass of the atom of element. And option D is electron, that is just revolving round, of course, round. So the correct answer is option D, electron. Question number 30. An element will readily form an electrovalent compound if its electron configuration is what? First, we must know what electrovalent compounds are. Electrovalent compounds are compounds that are formed when there is transfer of electron, usually from the metals to the non-metals. Okay, there's this transfer of electrons, because the metals usually are electron rich, so they will always donate electrons to the atoms of element that are what? That are deficient, okay, of electrons. So they are rich in electron, they can give out easily to the non-metal. Usually transfer of electrons from metals to non-metals. Other words, we can call electrovalent compound ionic compounds, okay, because it involves ionic bonding between the metals and the non-metal. So what we are going to look out for among these options now should be a metal. Which configuration? The electric configuration has metal, because it's an element will readily form an electrovalent compound if its electron, okay, configuration is what? So we should have a metal and a non-metal, highly electropositive elements and highly electronegative elements. So either of the two that we have. Let's look at option A. Says 281. 281, that is 2 plus 8, that's 10 plus 1, that's 11. So which element has electron configuration of 11? the atomic number of 11 is what? Is sodium. So sodium is this. Sodium, of course, if you agree with me, it's a strong metal, okay? Very reactive metal. So it has Na11. So which means this one electron can be given out easily because this 2 occupies the first shell completely filled, 8 occupies the second shell completely filled, and then this one is just 1 on the third electron. So it can easily give out, donate this electron to what? To the non-metals that needs 1. Okay, that's highly electronic, like your chlorine, that is 287, that needs just 1. So this can combine with chlorine to give out this 1 electron to it. So this one is very correct. Let's look at option B. We have 284. Yeah, we have 2 in the first shell, 8 in the second shell completely, 4 in the fourth shell. So this one now has 4 electron, valence electron outside. So which means that it can give out 4, but it is very difficult for this to give out 4 because 4 is a whole lot compared to this, okay? Because this 4 can actually, instead of giving out this 4, this element will either prefer, let me get another atom of the same element like me, then both of us will what? We share together, okay? We become molecule. Or it will say, okay, let me look for an element that also has electron that is 4, then both of us can share together to make it. Instead of giving out a O4, 4 is so big, okay? It's easier to give out 1 than to give out 4. So let's look option C, say 288. Of course, 288, first shell, the maximum number of electrons that must be there must be 2, is filled. Second shell, 8 filled. Third shell, 8 is also filled. So this one will not even give out or receive from anyone because it is satisfied, it is rich. Of course, this should be what? The noble gases. 28, that's 10 plus 3, that's 18. So that is your argon. Argon has atomic number of 11, of 18, so it will not undergo any form of giving or receiving any electron from anywhere. So this also will not. Okay, then the last option is option D, 285. We have 285, just like in this case. This is filled, first shell is filled, second shell is filled. It is easier. This is 5. This one is looking for just 3 to complete the 8. The octet rule also. Okay, so it is easier for you to look for one that has 3 to combine with it, okay, or look for another element like it than for it to say, oh, I'm going to give out a whole 5 electron. It is so difficult. So among all of these options now, the most appropriate, the element that will readily form an electrovalent compound in if its electron configuration is what? 2, 8, and 1. So option A is the correct answer. Now let's move on to question number 31. A heterogeneous mixture can be defined as any mixture. Of course, we have heterogeneous and then we have homogeneous. If it is homogeneous mixture, it means that the constituents, okay, the composition of that particular solution or mixture are the same, okay? You can't distinguish one from the other one. They are all, when you mix them together, you can't say, oh, this is this and this is the, in this case now we have heterogeneous mixture. A heterogeneous mixture is one that the composition are not uniform, are not the same. For instance, now if you have oil in water, okay, that is a heterogeneous mixture. You can see the oil separately, you can see the water separately, you can distinguish because usually it has more than one phase. That's about 2 phases, okay? We have the phase where we have the oil in water or water in oil, whichever way, you can separate between them, okay? That is heterogeneous mixture. But if it is homogeneous mixture, if you have your water in ethanol, okay, you discover that when you mix water in ethanol, you cannot tell, apart from maybe trying to smell, to see. If you look at, you will think it's just water because it's colorless, there's no 2 phases, okay, like we have in heterogeneous, and then the constituent will be the same. But in terms of heterogeneous mixture, the constituent will not be. Option A says of a solute, of any mixture of a solute and a solvent. Of course, this is going to give us what? A solution, but that does not depict heterogeneous. Option B says whose composition is uniform. If the composition is uniform, then it is what? Homogeneous mixture, not heterogeneous. Option C says whose composition is not uniform. Of course, that is heterogeneous. And option D says formed by solids and liquids. No, so the correct answer is option C, whose composition is not uniform. On to question number 32. The pressure of 100 cm cube of oxygen at 35 degrees Celsius is 750 millimeter mercury. Okay, so of course, you know, this is volume V1, this is a T1, and then this is a P1. Okay, so what will be the volume of gas if the pressure is reduced to what? 100 millimeter mercury. So this is P2. We have to find V2. without changing the temperature. So if we are not changing the temperature, it means temperature remains 35 degrees Celsius. If the temperature remains 35 degrees Celsius, it means the temperature is constant. And if the temperature is constant, it means that what? There's a relationship between pressure and volume. So which means that is what? Boyle's law that is in place. Now don't forget this is JAMB, and then you have to work smart. Okay, you can go on and begin to solve P1 V1 over T1 equals to P2 V2 over T2, meaning that you are using this as a T1, and then because it may not change, then for T2 you also use this. But if you are working smartly, okay, you don't need to waste much time here. What does Boyle's law state? It says that the volume of a given mass of gas is inversely proportional to the pressure, provided temperature remains constant. So it's looking at a relationship between P1 and what? V1. P and V. Pressure and volume. Now, if you look at the values that are given, they are intentional. Remember, I said you must learn how to work so smart. Okay, minimize your time and spend lesser time on simpler questions, and then spend more time on their questions that will take more time. Look at this question. We were told that the pressure of 100 cm3. Let's go to the board and let's analyze. We have so let's just write the given parameters we have there. We're told that we have the V1 is actually 100 cm3. Okay. Then we have the T1 is 35 degrees Celsius. Of course, if we change that to Kelvin plus 273, that is going to give us, that is 8, that is 0, and that is 3. 308 Kelvin. And then we have P1, of course, was given as 750 millimeter mercury. Okay. Then we have V2, of course, is what we have to find. What would be the volume of the gas? T2, of course, is still the same, 35 degrees Celsius, of course, which is 308. We've done that already, Kelvin. And then we have P2 was given as 100 millimeter mercury. Now, already we said that temperature is constant, so which means there's no point using this. So the relationship is actually between pressure and volume. P1 V1 equals to P2 V2. For me, I have seen the value. Don't forget, as scientists, you have to be very observant. I've seen the value of volume to be 100, okay, and then pressure was 750. Now, pressure, P2 is now 100, the same 100 you have here. So definitely you should know, since they are inversely proportional, if volume is decreasing, pressure must increase. Or if pressure is decreasing, volume was what? Must increase. They are inversely proportional. So now we have the same value. V1, when V1 was 100, P1 was 750. Now P2 is 100. What will V2 be? It's 750. There's no point wasting time. But if you are not so sure, please go ahead and solve. But I'm only saying that you should know the smart part of the question, okay, where you can be able to what? To bring in that V1 is 100, was 100, P1 was 750. Now P2 is 100, the same 100 here. Then what will V2? V2 will be the same what? 750. But let's try it so that we can see. So that is working smart. If you do that, you just pick 750, you pick answer. But let's go with this. P1 is what? That's 750 times okay, I think we can just go ahead, since we want to find V2, so we can make V2 is sort of a formula. So we have P1 V1 all over what? P2. So if you put in the values here, P1 is 750 times V1 is 100 over P2 is 100, of course. So you can see now that 100 cancels 100, and then we have 750 no, that's not millimeter, that's V2. Okay, so that is a cm cube. So you can see when V1 was 100, P1 was 750. Now P2 was 100, V2 will be 750. Inversely what? Proportional. So let's look at the options we have on the screen. 750 cm cube. Option D happens to be there. So the correct answer here is option D, 750 cm cube. Now let's move on to question number 33. Treatment of cancer. Detection of leakages in water means detection of the ages of ancient tools. In fact, once I've seen treatment of cancer, I already know it's something that has to do with radioisotopy. Okay, so we have a detection of the ages of ancient tools, and we have preparation of drugs. So the question says, which combination of the above refers to the uses of radioactive isotopes? Radioactive isotopes, don't forget, they can be used, okay, in treatment of cancer. They can be used in detection of leakages in water mains. Yes, that is what they can do as well. Then they can also be used in detecting the ages, how old the ancient tools, the tools that are being used, how old are they? Okay, yes, the isotope, radioactive isotopes can also help us in time. And the last one, preparation of drugs. Yeah, we use them in preparing drugs. Okay, before we talk about synthesis of drugs, radioactive isotopes are used in making. Don't forget that we use it in treatment of cancer. So there are drugs that will help to cure this cancer. So in preparation of drugs too, radioactive isotopes find application there. So which means we might figure 1, 2, 3, 4, all of them are correct. So let's look at the option. We have this. Okay, 1, 2, 3, 4. So the correct answer is option D. Now let's move on to question number 34. What is the valence shell electron configuration of the element with atomic number 17? Please, you have to be careful in your approach to this question. There's a key word there. What is what? Valence shell electron. Valence shell electron. Please, it's very important. You must be careful as to choosing what the right answer. Many students, because I've seen some students answer this question and then they went for electron configuration of atomic number 17. That is not what the question says. It says that valence shell electron are not the same. When you talk about electron configuration, you are talking about how the electrons are arranged in orbitals, okay, electronically, how they are configured in the s orbital, in the p orbital. Then you'll be talking about 17, okay, having of course that is a chlorine. So we have 1s2, 2s2, 2p6, 3s2, 3p6. Let's see that 2 plus 2 is 4 plus 6 is 10, 10 plus 2 is 12, 12 plus this is 18. Okay, so which means we can have this. So this has to be 5. Let's see, 10, 17, because it is 17. So adding up those number of electrons is 7. So this is what should be the electronic configuration or electron configuration of the element having atomic number 17. So if you look at the option, we have 1s2, 2s2, 2p6, 3s2, 3p5. Which is this? This is not the answer. This is only what? Saying that this is the what? Electron configuration. But the question says, what is the valence shell? Now, when we talk about valence shell, we are talking about the electron in the outermost shell, the last shell. That's the valence, the valency. Okay, don't forget, it has to be with what? The combining power of that. So the valence electron. So if you have 17, for instance, 17 should be 2, right? 8, right? That is 10 because 17. Then we have 7 here. Okay, so which means this one is going to be in the last shell. The first shell is going to take 2, the second shell is going to take 8, and the third one is going to take 7. So this is the valence electron, so which is 7. So what you're going to do is look at the options. Which one has its what? A configuration that amounts to what? To 7, which is that. So if you look at option A says 1s2, 2 plus 2, that is 4, plus 6, that is 10, plus 2, that is 12, plus 4, that is 16. Of course, that is less than this. So this, of course, is eliminated. Option B says 1s2, 2s2. So like I said earlier on, this is going to be the electron configuration, but not the valence shell electron. That's to do with the shell. So option B is also not. Please don't go for it was put there by the examiner just to see if you actually understand valence shell and what valence shell and electron configuration. So this is electron configuration. This is not valence shell. Okay. Option C says 2. Okay, 2 plus 6, that gives us 8. So which is not what? 7. And option D says 2 plus 5. Of course, that is what? That is 7. So 2 plus 5, this aspect, that's the valence shell electron, which is what? 7. So the correct answer is option D. Do you know you can take practice questions on our simulated JAMB CBT past questions? All you need to do is to click on the link in the description below that takes you to the Myschool website. There you'll be able to download the Myschool mobile app on your Androids and the Myschool software on your laptops and computers. Please go ahead and start practicing. Now let's move on to question number 35. The density of a certain gas is 1.98 grams per dm cube at STP. Take note, at STP, standard temperature and pressure. What is the molecular mass of the gas? When we talk about molecular mass, we're also talking about the mass of the particular gas that is. But you will first agree with me that the density of a certain gas, density is actually given. Let's look at the board. Let's go to the board. We're given, okay, the density, I will use the density, okay, usually we have rho, they use rho for the symbol, was given to be 1.98 gram per dm cube, okay? And then we're given, that is all, at STP. So what is the what? Molecular mass. Molecular mass. But also remember that density is actually equal to mass over volume. Okay, that is our density. That's the formula for finding this thing. Density equals to mass over volume. But in this case, we are looking for what? Molecular mass. So we can replace molecular mass with what? With the mass, and then volume. Don't forget that we're told that the density of the gas at STP. So if it is at STP, we are looking at what? The molar volume, which is always a constant. That is what? 22.4 dm cube. So which means that we can say that we can rephrase this to be density equal to molecular mass. Of course, it's a mass, molecular mass all over molar volume. This is volume. It can be molar. We can change it to molar volume. Why? Because it was given at STP, and the molar volume of all gases at standard temperature pressure is a constant, which is 22.4 dm cube. So you can just move ahead now and have it. So if you make this subject of the relation, so molecular mass now is going to be molecular mass is equal to, of course, over 1 cross multiply 1 times that. So we have density multiplied by molar volume. So by the time you multiply that together, we have density was given to be 1.98 multiplied by molar volume was given. Of course, we know that it's a constant at 22.4 dm cube. By the time you multiply this together, we are going to have 44 point. We have about 3. Okay, 44.35 terabytes. Okay, that's going to be in gram. So if you change this to 112, okay, that's two significant figure. Of course, if you round this one up, this is not up to, that's 0, so you add it up. So we have about 44.0 gram. Okay, we can have that as a molecular mass. So now let's go back to the screen and see the options we have. The option A says 44.0 gram, 54 this and this. So the correct answer is 44.0 gram. Option A is the correct answer. I believe you are enjoying this content. If yes, please don't forget to click on the like button, hit the subscribe button, and finally tap on the notification bell to keep you informed once we upload our next video. Now let's move on to question number 36. When pure aluminum metal is heated to red hot in the presence of nitrogen gas, the compound formed is what? Of course, when you have pure metal like aluminum, okay, that is heated, you heat it red hot and you pass it over the nitrogen gas, a chemical reaction is going to take place between the aluminum and the nitrogen gas. Okay, so what happens is we are going to have, this is your aluminum metal, okay, reacting with nitrogen gas. That's the chemical reaction that is going to take place. We are going to form aluminum nitride. So we have ALN. Yes, that's what we're going to have. Let's see. To balance up this equation, if we have 2 here, okay, so nitrogen is 2 now, aluminum is 2 here, so we have 2 here. I think the equation is balanced. This is the gaseous state. This is aluminum metal, because that's solid. Then we have aluminum nitride here. That's that. So we have 2 aluminum, most of aluminum metal passed through. Okay, it is heated red hot, and then it is passed through a nitrogen gas. Reaction will take place between that aluminum and this nitrogen, because then we have aluminum nitride, so which is 2 moles of ALN. This is what we're going to have. Okay, it says form is that, so we have option A is Al2N, no, Al2N2, no, ALN, yes, and then so the correct answer is option C. Now we are moving on to question number 37. A dense white film is formed when ammonia gas reacts with. We know that when we in the lab, if you get your ammonia, okay, you get it closer to a particular acid, a gaseous of a particular gas, what happens? You discover that there are white fumes, and this white film is actually showing that a substance that is ammonium chloride is formed. So, but the chloride is coming not from this Cl2, but it's actually coming from what? HCl. Please, this HCl is not hydrochloric acid, because you see gaseous here. Once you see gaseous, it means what? It is hydrogen chloride gas. Okay, even though both the gaseous state and then the aqueous state acid actually has the same formula, but their names are not. Once you see the state, this is what? Hydrogen chloride. But if it is aqueous, it becomes hydrochloric acid, even though it is the same HCl. So this reaction is what we call it is a neutralization reaction. Let's look at the board. It's a neutralization reaction because we have an acid and a base there. So we have ammonia, reacting with HCl, okay, that's hydrogen chloride. This is gaseous, okay, and then we have this could be aqueous, gaseous as the case may be. So we have NH3. We have that they are going to have ammonium chloride. That's to show the presence of what? Of the ammonia. So this is your acid. Of course, it's gaseous, but it is an acidic gas. And then this one is acting as a base. I said this neutralization because this is a base. Now this ammonia is going to accept an electron from this acid here. Okay, so a proton is going to accept this proton. So a proton acceptor, that's your base. Okay, the bases will accept protons, and acids usually are proton donor. Okay, remember the Lewis base. So this ammonia is accepting one proton from this acid to become what? Ammonium here, chloride, and then you have that. So this is your base, and then this is acid. This is your acid. So it's in neutralization reaction because we have what salt here eventually. Okay, to have that is a form of neutralization reaction. So the presence of white fumes is what shows that what ammonium chloride has actually been formed. Ammonium chloride. So the white fume is actually HCl reacts with that. So let's move on to the screen. So a dense white fume is formed when ammonia gas reacts with not oxygen, not its hydrogen. Of course, if you react to reaction, you know you are not going to have a salt that's going to have those white fumes. We have this, and then we have this. So the correct answer is option D, HCl. Now on to question number 38. We have nitrogen gas reacting with 3 moles of hydrogen to give us 2 moles of ammonia. Okay, we have that. Of course, this is a formation of ammonia, and that's what we call the ABA process. In the ABA process, we have nitrogen reacting with hydrogen gas to form what? Ammonia. Okay, of course, that is an exothermic reaction. You can see here delta H is negative 90 kilojoules. Okay, so this is what an exothermic reaction. Now the question says, in the equation above, the yield of ammonia can be decreased by, how do we decrease the yield of ammonia? Let's look at the option. Option says increasing the pressure, removing the ammonia as it is formed, increasing the temperature, adding a catalyst. Now don't forget that in terms of the yield of ammonia, there are 3 things we can look at. We can look at the effect of temperature, is it increased or decreased? We are looking at the effect of pressure, and then we're looking at the effect of concentration. Those 3 things can actually determine the amount of ammonia that is produced. Now, in this case now, if we look at the effect of pressure, don't forget, according to Le Chatelier's principle, if there is an effect, there is a change in the equilibrium position of a reaction. What happens? The chemical system will adjust itself, okay, in order to annul or cancel the effect that is brought about by the changes that was brought about by the effect of the changes that was brought about. So in this case now, we have 1 mole of nitrogen here. Don't forget, we are looking at pressure now, and for pressure we'll be looking at the number of moles of the gaseous substances, both on the left hand side, on the right hand side. So let's look at it. We have 1 mole here and 3 mole here. So total number of moles is 4 moles on the left hand side. That's the reactant side. On the right hand side, we have 2 moles here. And according to Le Chatelier's principle, if we are going to have being favored, the forward reaction, more of this to be produced, okay, what we have to do is we look at the number of moles. The side that has the lesser number of moles will be favored by an increase in pressure. If you increase pressure, the side that has lesser number of moles will be favored. Now we have 4 moles here, we have 2 moles here. So 2 moles is lesser. So which means increase in pressure will increase the yield of ammonia. Yes, increasing the pressure. But don't forget, it's saying that what? The yield of ammonia can be what? Decreased. So we are looking at what? Reducing the amount of ammonia from not increasing. So if it were to be increasing, the yield of ammonia be increased, increasing the pressure would have been the perfect answer because we have lesser number of moles on this side. So increase pressure. So if you decrease the pressure, the equilibrium will shift to this side. So more of this side that has this will be formed. So which means increasing the pressure is not going to work. So we eliminate that. Option B says removing the ammonia as it is formed. If you remove the ammonia as it is formed, that means you'll be producing more of the ammonia. So the ammonia yield will be what? Will be increased, not decreased as in this case. So this is also what? Eliminated. Option C says increase the temperature. Now when we are looking at temperature, we consider what? The change in enthalpy. That is your delta H. Is the reaction endothermic or exothermic? Okay, so now in an endothermic reaction, that's if delta H is positive. In an endothermic reaction, increase in temperature will favor the forward reaction. So more of the what? Of the reactant, of the product will be formed if you increase it, and if you decrease the temperature, more of the what? Reactants will be formed in an endothermic reaction. Okay, but if it is exothermic reaction, if you increase the temperature in an endothermic reaction, you are going to have more of the reactants will be formed. Okay, if you increase the temperature, more of the reactants will be formed, and then if you decrease the temperature, more of this will be formed. Okay, so which means if you increase the temperature, you will form more of this and less of this. But if you decrease the temperature, you will form more of this and less of this. We are looking at a situation where we will form less of this, decrease in the yield of that. So which means that in an exothermic reaction, a decrease, an increase in pressure, or sorry, an increase in temperature will form less of this. Okay, less of this, the yield of this will be what? Will be decreased if you increase the temperature. And option C says increasing the temperature, so which means this is correct. Option D says adding a catalyst. If you add a catalyst, you are just going to do what? End up speeding up the rate of reaction. It's not going to increase the yield of ammonia. So based on our analysis, the correct answer is option C, increase the temperature. Now we are moving on to question number 39. The gas that can be dried using concentrated tetrahydrosulfate 6 acid is what? That's your H2SO4, conc H2SO4. You will agree with me that concentrated hydrogen tetrahydrosulfate 6 acid or tetrahydrosulfate 6, or what we call sulfuric acid, is actually a hygroscopic substance. And hygroscopic substances are usually substances that what? That has tendency what? When you expose them to the atmosphere, what happens? They will absorb moisture. Okay, they will absorb moisture. So that is why they are used often as drying agents. And we have different drying agents. We have quicklime is one of them. We can use quicklime. You can use calcium hydroxide. We can use conc H2SO4. We can use silica gel. So, but there's a particular drying agent that can dry all gases, that has no limitation, and that is what? Silica gel. Silica gel can be used to dry up any gas at all. That's why you discover that they put them in shoes. The new shoes you wear, okay, that you just get, you can see them in that paper. That's your silica gel. The white substance, of course, it's poisonous to the mouth. So it can what? It has tendency. Now the question says the gas that can be dried using concentrated tetrasulfate 6 acid is what? Tetrasulfate 6 acid can be used to dry all manner of gases apart from ammonia and as well as what? Hydrogen sulfide. Okay, hydrogen sulfide and ammonia are the two gases that this conc H2SO4 can, but any other gas at all it can dry. So let's eliminate option C, okay, and option D. They are eliminated. So we are left with hydrogen bromide and sulfur oxide. Now the issue is that hydrogen sulfide, yes, can react with tetrasulfate 6 acid, okay, and then instead of drying up the moisture that is present in that gas, what happens? It reacts with it and form SO3. That means in this case of hydrogen sulfide actually, okay. So hydrogen bromide has a limitation here, and then you have this. So we have sulfur oxide now. Sulfur oxide is among these options. Now it's the best option. Now is the gas, that's SO2. Actually, yes, SO2 is the gas that can be dried using concentrated tetrasulfate 6 acid. So the correct answer is option B, sulfur oxide. Now let's move on to question number 40. We have a reaction here, ammonium chloride. Okay, this is a reversible reaction, okay, to form ammonia and HCl, okay, reversible. We saw a question like this before where we talked about ammonia gas brought closer to hydrochloric acid to form this white fumes, okay, but this time it is what? The reversible reaction. The reaction above can only attain equilibrium if what? If what? Option A says a gaseous reactant is added. If you add up a gaseous reactant here, of course this is the reactant, you are not going to form this. It's going to alter that reaction. So option A is not correct. Option B says one of the products is removed. If you remove one of the products, then you'll be forming the other products, and that is not our aim, okay? Because as the reaction continues, as you remove this, you will not have this. Is supposed to be a reversible reaction, so option B is not also correct. Option C says it is in a closed system. Well, what is a closed system? In a closed system, usually the reaction will continue. The reaction upon the time it gets to a time where the concentration of the reactant that we have there begin to increase, okay, just like the concentration of the what of the product also continues to increase. So the reaction continues over and over and over until it gets to a point where the rate, okay, of the forward reaction becomes equal to the rate of the of the backward reaction. So once that happens, the reaction can tend towards equilibrium. So usually in a closed system, equilibrium position tends towards equilibrium position. Yes, equilibrium position can be attained easily with what? With a closed system, because nothing is evolving, nothing is going out of the system into the environment, and nothing is also coming into the environment. So if you have like this reaction now where we have fumes or we have gases, they are all in that closed system. So the reaction will keep going on and on and on until you have an equilibrium position. So yes, we can have equilibrium if it is in the closed system. If it is in an open system, you can't have that. So the correct answer here is option C. It is in a closed system. Question number 41. The most suitable metal that can be used as lightning conductor is what? The suitable, we would have said the most suitable should have been what? Or the most effective. Okay, the most effective metal usually that is used as a lightning conductor is actually silver. Okay, it's silver. We have silver, we have copper, we have iron, we have aluminium. Okay, it is not iron, it is not aluminium, it is what? Silver. Silver and copper, usually both of them are effective, okay, metal that can be used as lightning conductor. But we will not go for silver, even though it is the most effective. But the question says the most suitable. Now, if both of them are actually effective, okay, for what? That can be used as lightning conductor, but the most suitable usually is for copper, because this silver is actually so expensive to use. So the most suitable, if we have two options and then we have one that is cheaper and can still do the same function, okay, just as this, I think it is wise enough to us to go for the one that can do the same function as this, and then it is cheaper. Okay, so in lightning conductor, what can be used? The most suitable metal that can be used as lightning conductor, most suitable. Okay, the most effective should be silver, but the most suitable, and it is effective as a lightning conductor. It can conduct in terms of conduction of heat, then also in terms of affordability. Okay, we are looking at it also, affordability, option B, which is copper, tends to be more suitable than that. So based on that, the correct answer is option B, copper. Now we are moving on to question number 42. We have a diagram here, and we have curves, different curves here. We have one here, this is X sloping down. We have a Y moving this from this point. Then we have Z, okay, from the origin, moving this way, that is slope. And then we have the one that is moving uniformly, that is R. So we have a plot of ln K, okay, that is natural log of K against the reciprocal of T, inverse of T. So the question says, in the diagram above, which of the curves illustrates Arrhenius law? When we talk about Arrhenius law is looking at plotting a graph, okay, between natural log K and then the reciprocal of temperature, absolute temperature, 1 over T. Okay, looking at the relationship, and then eventually we have it a slope as the EA over R. We have EA is the what? Activation energy. Looking at the relationship between that. Let's look at the diagram that illustrates, an example that illustrates the Arrhenius law. So this is a diagram that illustrates, just an example, okay, just to illustrate, to show the Arrhenius law. So you can see on the y-axis, we have the ln K, that's the natural log on this, and then on this x-axis, we have 1 over T, that's the reciprocal, okay, the inverse of what? Of temperature. So which means they are inverse proportional. So on y, changing y, we have this value. So we have this slope, you can see it coming down. Now, the slope actually is the negative of EA, that's activation energy, over what? Over R, because R is a constant, and then we have this EA is actually change in y-axis, okay, this minus this, all over change in x, this, okay, this, like this, minus this. That is your slope. Change in y, y2 minus y1 over x2 minus x1, that's the slope. So it's also equal to the negative value of what? The activation energy over the what? The R, the constant. So you can see this is how the Arrhenius reaction, the Arrhenius law now, okay, this guy, see the slope, how it comes down from this way, from your left moving to the right. So now let's move on back to our question to pick the correct answer. So from what we just saw now, among all of this curve now, which one has the what illustrate the Arrhenius law? We saw that graph coming this way, okay, sloping for that, of course, that is x. So we have y0 and x. So the correct answer is option D, curve x. Question 43. The most abundant element on the Earth's crust is what? Please, you have to be careful here. Don't get confused about the abundance in air. Yes, when we talk about air, we say air is a mixture of gases, and we know that nitrogen actually has about 78% composition of the mixture of air. So you can see we have nitrogen here. So if you pick nitrogen, you will be wrong, because we're talking about the most abundant element on the Earth's crust. When we're talking about Earth crust, we're talking about the different aspects in biosphere. Of course, in biology, we look at the biosphere, which are the atmosphere, made up of the atmosphere, made up of the hydrosphere, made up of the lithosphere. So all over, in the water, on the land, okay, in the air, in the atmosphere. In the atmosphere, we have nitrogen having the highest, okay. But in the old Earth crust, okay, we have nitrogen, we have hydrogen, we have oxygen, we have fluorine. Even in the water, we have oxygen. Even though it has 21% in air, we have more in water, and then we can also have it on the land. Okay, so we have that. So based on that, I think oxygen has about 46%. Let's look at the chart. Yes, let's look at the chart, the diagram, to be able to protest this point. So this is the elemental composition of the what? Of the Earth crust. Okay, you can see silicon here about 28%. Of course, that's composing of your made up of your sand. We have aluminium here 8%. We have iron here 6%. Magnesium 4%. Calcium is 2.4%. Other elements we have 5.6%, and then we have almighty oxygen. You can see that here. Look at it, about 46%, almost 50% of the air. So the Earth crust actually contains more of the hydrogen, which is about 46% in composition. So oxygen, not nitrogen, not chlorine, not fluorine, not any other one. It is what? Oxygen. Let's move back to our options so that we can choose our right answer. So the most abundant element on the Earth crust is oxygen. The correct answer is option C. Now let's move on to question number 44. Metalloids are also referred to as what? Metalloids have characteristics that are in between the metals and non-metals. Okay, they have some features that characterize them. Like some of them, even though they are not metals, okay, they can still conduct electricity and heat. Then we have like germanium, we have arsenic, we have carbon, okay, in group 4 we have silicon, okay, those are examples of elements that actually they act as metals. They have some properties, and they have some properties that are also what? Non-metal. So they are in between. In the periodic table, we refer to them as the bridge element between the metals and the non-metals, okay, we have them just like that. So because they have some characteristics that are metallic, we refer to them as semi-metals. So let's look at the option. Option A says semi-metals. That's correct. They are not metals, they are not colloids, they are non-metals. They are not non-metals. So the correct answer here is option A, semi-metals. If you have any question bothering your mind at all, please feel free to ask. All you need to do is to click on the link in the description below that takes you to the Myschool website. There, you'll be able to ask your question, and solutions will be provided within the shortest period of time. Now, let's move on to question number 45. The ores that can be concentrated by flotation are what? Now, when we talk about flotation, some cases we call them froth flotation, F-R-O-T-H. Now, flotation is a concentration method, okay, whereby we have valuables. Of course, don't forget when we talk about ores, we have valuable elements or nutrients or substances that are present in that mixture, okay, just like in the raw state. Like we have the aluminium oxide, we have your bauxites for aluminium, we have the hematite, okay, for your iron, we have, and so on and so forth, cryolites for aluminum, and so on. So those are ores. Now the ores that can be concentrated, it is not all ores that can be concentrated. Don't forget, we talk about concentration method. That is what flotation has to do. What happens? Substances are brought into the ore, okay, to react with the ore, and then usually once it's brought in, it will now form air bubbles. The valuable metals also, or the valuable substances or elements that we wish to separate will be what? Will form air bubble, okay? That's what we talk about, the flotation, and then we float, so we'll be able to to gather them, and then we concentrate the valuable elements. And usually it is for ores of sulfur. Sulfide ores usually are the kind of ores, like I said earlier on, it is not all ores that can be gotten, that can be concentrated by this flotation method. They are especially the sulfide ores, usually that contains the zinc, they contains the ores of lead, and so on and so forth. So the ores that can be concentrated by flotation are not the nitrite ores, not the oxide ore, not the non-metals ore, but the sulfide ore. So based on that, the correct answer is option B. Do you have any better steps or better explanation to all the questions we have solved so far? Please feel free to share with us. All you need to do is to go to the comment section, indicate the question number, and then the solution you wish to share with us. Now let's move on to question number 46. The property used in the industrial preparation of nitrogen and oxygen from air is what? Property used in the industrial preparation. That means we want to separate them. Don't forget that both nitrogen and oxygen are found in air, and then we said air is a mixture of gases. We have about 78% of nitrogen, and then we have about 21% of oxygen in the mixture of air. Okay, so how do we separate them? Now, the separation is usually done by no other method, by fractional distillation. We refer to it as, first of all, the first process is to liquefy the gas. Okay, we say liquefaction of air, of gas. Okay, when you liquefy it, as the temperature begins to reduce and the pressure increases, what happens? It cools down. As temperature begins to cool down, what happens? You can be able to separate the different, gases. The nitrogen, okay, you separate it, and then you have the oxygen also being separated through fractional distillation, of course. And like I said earlier on, it starts with the liquefaction of the air first. When you liquefy the air, okay, it becomes colder, and as the temperature begins to reduce, and then the pressure increases, what happens? You can begin to form your oxygen and nitrogen. So the correct answer here is not rate of division. Don't forget that fractional distillation works on the principle that is separated by a boiling point, differences in boiling point. Okay, that's the principle with which the fractional distillation work on. So both of them have different values of boiling point actually. So the rate of diffusion is not the answer, density is not the answer, solubility is not, but it is based on boiling point. So the correct answer is option C, boiling point. So let's move on to question number 47. Question 47. In a flame test for calcium, the flame appears what? This is one of the confirmatory tests of metals. Different metals have their colors that they produce when they are brought into the flame. Maybe let's say Bunsen burner, okay? So if we are talking about calcium now, if you get a salt, okay, that contains calcium ion or calcium metal, what happens? Put it in your spatula, then bring it on a non-luminous Bunsen burner flame, okay? You light it, and then like the one we have in our laboratory, in our schools. So you put it, and then you put it on top or inside the flame. Bring it in contact with the non-luminous Bunsen flame. What happens? You see a red color. A brick red color is what you are going to get. But once you bring a blue glass, you put it this way and try to view it, the color is going to change to green. What you will see will be a green color. Take note, when you bring it with your naked eyes, bring it in contact with the flame, what happens? You have a brick red color. But if you view it using a blue glass and view the flame, you discover that the color eventually changes to what? To color green, so which is not. So let's look at the options now. Option A says, okay, say the flame test for calcium, the flame appears green when viewed through a blue glass. Yes. It will, once you view it with a blue glass, it's going to appear as green. Option B says blue when viewed through a blue glass. No. Option C says orange red when viewed through a blue glass. No. Option D says brick red when viewed through a blue glass. It's going to be brick red with our naked eyes, when viewed with our naked eyes, not with blue glass. Once you use blue glass, it's going to give us a green color. So based on that, the correct answer is option A. Question 48. Which of the following alloys contain iron? Option A says duralumin and steel. When we talk about duralumin, of course, we know it contains, as the name implies, aluminium. So the major alloy there is actually aluminium, so not iron. We are looking at the one that contains iron. So this one does not contain iron. Steel, of course, yes, we know steel contains the iron alloy. Yeah, so this one is correct, but this is aluminium. So because of that, option A is eliminated from the options. Option B, we have brass and bronze. Neither of them actually has iron contained in them. Of course, we know your brass is an alloy of copper and zinc, okay, and then your bronze is the alloy of copper and tin, okay, makes up your what? Your bronze. Those are alloy of brass and copper and zinc make up that, and then the bronze is made from what? Copper and tin alloy make up the bronze. So there's no way we have iron alloy there. So option B is also eliminated. Option C, we have steel and permalloy. When we talk about steel, we already said steel has iron present in it as alloy, and permalloy. Permalloy is actually a magnetic substance that actually contains nickel. Nickel, of course, you know that nickel is a transition metal. Nickel, and then contains iron as well. Okay, in the proportion 80% of nickel, and then we have 20% of iron make up the permalloy. So we have iron present here as alloy in permalloy and also present in steel. So that is correct. Let's look at option D. Says soft solder and duralumin. None of them actually has iron present in it. We have duralumin. Duralumin does not have, okay, duralumin already contains what? Aluminium. Okay, not this. So both of them does not have this. So this is also correct, not correct. So the correct answer among this is actually option C, steel and permalloy. Now we move on to question number 49. To obtain pure carbon 2 oxide, that's your carbon monoxide, from its mixture with carbon 4 oxide, the mixture should be what? First, you must pass the mixture of carbon 4 oxide, you must pass it through red hot carbon. Okay, when you pass it through red hot carbon, what happens? The carbon 4 oxide, CO2, becomes reduced to CO, okay, carbon monoxide, carbon 2 oxide. Pass a red hot carbon, okay, over the carbon 4 oxide, what happens? The carbon 4 oxide becomes reduced to carbon 2 oxide, which is your carbon monoxide. But we still have some CO2 that are uncharged there. You know, as you are passing it through the red hot carbon, the carbon 4 oxide becomes charged. So there are still some carbon 4 oxide that will remain that are uncharged, okay? They will form impurity because we want to get pure substance of what? Carbon 2 oxide. So what we need to do is just bring in your carbon 4, concentrated sodium hydroxide, that is NaOH, okay? Once you bring that in to it, that will be able to what? To get for us. You bubble it through sodium hydroxide. Once you bubble it through sodium hydroxide, we have a pure substance of this carbon 2 oxide. The uncharged carbon 4 oxide would have been what? We have been removed by sodium hydroxide. Sodium hydroxide. When you bubble it, we have that option. A says passed over heated copper 2 oxide. No. Option B says bubble through water. No. Option C says bubble through concentrated tetrasulfuric acid. No. And option D says bubble through sodium hydroxide. So the correct answer is option D. Now let's move on to question number 50. The IUPAC nomenclature for the hydrocarbon above is what? We have CH3 here, CH, double. I think I need to redraw this on the board so we can have a clearer picture of what we are working with. We have CH3, we have the bonded to CH, then this is bonded to CH2, CH, then we have double bond, then we have CH2 here. Yeah, then we have on this carbon atom we have CH3 here. Okay, I think that's what we have. So we want to find the IUPAC nomenclature of this hydrocarbon. First and foremost, this is very easy. Okay, follow the rules and then you get it so easily. The first thing to do is what? To get our longest carbon atom chain, the longest among them. So let's count from here. We have 1, 2, 3, 4. Okay, that is one way. If we decide to pick it from here, 1, 2, 3, that is short. If we decide to go this way, 1, 2, 3, 4. So that means the longest is actually what? On carbon 4. Okay, carbon 4. We have carbon 4 carbon atoms. So, and if it is 4 carbon atom, which means 4 carbon atom means we have what? The name to be what? Boots. Don't forget boots for 1. If it's for 4, if it is 1, it is meth. If it is 2 carbon atoms, we have F. If it is 3 carbon atom, we have prop. If it is 4 carbon atom, we have but. If it is 5 carbon atom, we have prop. We have pent. If it is 6, we have X. Then ep, oct, and so on and so forth. So because we have 4 carbon atoms here, that the chain here we have but. Okay, but it would have been, is it butane? Is it butane? Is it butane? So we have a double bond here actually. So because we have a double bond here, which shows that it is an unsaturated hydrocarbon, not just saturated, it is an alkane. Okay, so which means alkane have carbon-carbon double bond. So because of this now, which means the name of this is going to end with ENE. But this carbon atom, on top of what carbon atom do we have it? If you label from here, carbon 1, carbon 2, carbon 3, carbon 4. So it's on carbon 4 if you go from this route. But the rule says that we go for the shortest route, okay? So if you are going from shortest, so you can count from this way, you can count from this. If you go from this way, the double bond is on carbon 4, which is actually long. So let's take it from the other route. So we have here, if you take it as carbon 1, carbon 2, carbon 3, carbon 4, okay? So this happens to be a shorter, okay, route compared to this. So on carbon 1, so we have the double bond here on carbon 1, so it's going to be -1 because we have double bond here, which is what? ENE. So that's the parent name. Here we have 1, 2, 3, 4, that is both double bond on carbon 1, but 1 in. Now we have a substrate group, that is the substrate functional group that we have here. Now we know usually that when we want to count for this, it should have been, we look at the shorter one, which is carbon 1, carbon 2. So which means this methyl group is on carbon 2. If you count from here, carbon 1, 2, 3. So this happens to be shorter. But since we have preference to this, since we have a double bond here, preference must be given to this double bond. And we already counted from here that this is on carbon 1, carbon 2. So it doesn't matter whether it is longer here or shorter. So already our counting is from here, carbon 1, carbon 2, based on what? This double bond that we have here, okay? Because it's stronger than what the other one. So carbon 1, carbon 2, carbon 3, carbon 4. So we can see here now we have a methyl group here. So we have methyl group on what carbon atom? Carbon 3. That's where this is attached to, okay? Counting from here, carbon 3. So this will be 3 methyl butane. So the answer is 3 methyl but 1 in or butane, okay, whichever one we have there. So we have butane. Please don't count from here and say this is 1, 2. We have a okay 2 methyl. Then you say we have a but this. You, of course, you can have options that we have there. I can see there. I'm saying 2 methyl but 3 in. Okay, here and then you have that. So the correct answer is 3 methyl but 1. Just follow the rules. You can get it easy. Let's move back to the screen and see what the IUPAC nomenclature for the hydrocarbon is. Option A says 1,2 dimethyl prop 2 in. That we are saying we have 3 as the parent chain. Okay, that is not it. We have 1,1 dimethyl prop 2 in. That's not correct. Option C says 2 methyl but 3 in. If it is 2 methyl butane in, we are saying that 2 methyl. We are saying that the methyl group CH3 is on carbon 2. That means it was counted from here 1, 2. And then you say this is 2 methyl, then you say but 3 in. Then you are making this now, carbon 1, carbon 2, carbon 3. You are saying this is on carbon 3. No, then this would have been longer. We are giving preference to double bonds. The shorter one should be on carbon 1. So it should be but 1 in. So the one that has but 1 in is actually option D. So the IUPAC nomenclature for the hydrocarbon above is 3-methyl but 1 in. Option D is the correct answer. I believe you enjoyed this content because I really did solving those questions. If you do, please don't forget to click on the like button, hit the subscribe button, and finally tap on the notification bell to keep you informed once we upload our next video.